Hi, welcome back to my channel. And in this video, I will talk about numerical integration. And before going to the code, I want to have the concept numerical integration. So this is our human analytical form, and this is the equivalent numerical form which we can input into the computer for computing. And for representing this analytical, we will have to get a lot of discrete values from which we can find the integration by summing up all of the discrete value. And we'll have the start point of the x from A, and the end point of the x value is B, the weight Wi corresponding to each value of the function at each discrete point along the x-axis depends on the integration rule or algorithm that we choose. They will have different kind of value, and then there will be a common factor. This common factor also depends on the algorithm or rule. They will have different kind of value. So let's see, we have 3 rules here. There are many other rules, but I just want to introduce those 3 rules. And the first one is the trapezoidal rule. As you could see, the common factor of the trapezoidal rule is totally different from the common factor of the other 2 rules. So that's why I say the common factor depends on the rule. They will have different kind of value. And for example, along this range, when x go from A to B, I compute an array containing 6 discrete values, and the x0 will have the value A, and the last value x, the 6th x value, will have the value B. So this is the range of x, and we need to find the weight for the corresponding fxi. So for example, if I want to find the weight of fx1, then I need fx0, let's say fx0, then x0 is here, so I look at this column of x0 and the last row. So 1 is our value of the weight 0. For the value of fx1, what is the weight? Again, we look at which x we compute the function value. So at x1, we look at the column x1 and we find, okay, 2 will be our value for weight 1, and etc. for the last one. So our last weight for fx6 is here, so 1 is the weight of w6. And we could do the similar deduction for Simpson rule and Simpson's other rule to get the corresponding value of each weight at each point by looking at the last row here. Okay, in order to go deeper into the code, I will choose only one of the rules to demonstrate inside the code, and trapezoidal is the one that I choose to demonstrate because all of the steps are the same for the other 2 rules. But before going into the code, I want to have summarized what are the steps necessary for doing the numerical integration. Of course, we also have 3 steps. Step 1, generate the x-axis. Step 2, generate the function. Generate the x-axis means we generate this array containing all of the values along the axis that we want to represent. And the second step is to generate our function. Generate our function means create this array, the array containing all of the values representing our function. If you want to know more about what is going on here, we could see the video about numerical differentiation. I say in detail about what they are doing here. But here I just want to have the summary of the steps before going to the code. And the third step is that we will write a function to computing the integration based on this generated array representing our function. So this is the array representing our function, and this is the array representing our x-axis. Okay, so this is the end of the introducing concept to numerical integration. So let's say this is the theoretical part, and for the practical part about the code, explaining the code, I will put it in the second video of numerical integration. So please watch it if you want to know more about the code. Also, there's the code link inside the second video, so wait for it. On the other hand, if you want to see the detailed explanation about the step 1 and step 2 relating to this graph and this one, please have a look at my video about numerical differentiation. So see you again. Goodbye.